Today is 29th March and I'm reading from Using SQLite by J.A. Kravich. So today we are going to continue reading chapter 5. We'll start with distinct keyword. The distinct keyword will scan the result set and eliminate any duplicate rows. This ensures the returned rows constitute a proper set. Only the columns and values specified in the select header are considered when determining if a row is a duplicate or not. This is one of the few cases when nulls are considered to have equality and will be eliminated. Because select distinct must compare every row against every other row, it is an expensive operation. In a well-designed database, it is also rarely required. Therefore, its usage is somewhat unusual. Order by clause. The order by clause is used to sort or order the rows of the results table. A list of one or more sort of expressions is provided. The first expression is used to sort the table. The second expression is used to sort any equivalent rows from the first sort, and so on. Each expression can be sorted in ascending or descending order. The basic format of the order by clause looks like this: order by, then the expression, then collation name, ascending or descending. The expression is evaluated for each row. Very often, the expression is a simple column reference, but it can be any expression. The resulting value is then compared against those values generated by other rows. If given, the named collation is used to sort the values. A collation defines a specific sorting order for text values. The ascending or descending keywords can be used to force the sort in an ascending or descending order. By default, values are sorted in an ascending order using the default collation. An order by expression can utilize any source column, including those that do not appear in the query result, like group by. If an order by expression consists of a literal integer, it is assumed to be a column index. Column indexes start on the left with 1, so the phrase order by 2 will sort the results table by its second column. Because SQLite allows different data types to be stored in the same column, sorting can get a bit more interesting. When a mixed type column is sorted, nulls will be sorted on the top, next integer and real values will be mixed together in proper numeric order. The numbers will be followed by text values with blob values at the end. There will be no attempt to convert types. For example, a text value holding a string representation of a number will be sorted in with other text values and not with the numeric values. In the case of numeric values, the natural sort order is well defined. Text values are sorted by the active collation, while blob values are always sorted using the binary collation. SQLite comes with 3 built-in collation functions. You can also use the API to define your own collation functions. The 3 built-in collations are binary. Text values are sorted according to the semantics of the POSIX memCompare call. The encoding of a text value is not taken into account, essentially treating it as a large binary string. Blob values are always sorted with this collation. This is the default collation. No case, same as binary, only ASCII uppercase characters are converted to lowercase before the comparison is done. The case conversion is strictly done on 7-bit ASCII values. The normal SQLite distribution does not support UTF-aware collations. rtrim, same as binary, only trailing right-hand whitespace is ignored. While order by is extremely useful, it should be used when it is actually needed, especially with very large result tables. Although SQLite can sometimes make use of an index to calculate the query results in order, in many cases SQLite must first calculate the entire result set and then sort it before rows are returned. In that case, the intermediate results table must be held in memory or on disk until it is fully computed and can then be sorted. Overall, there are plenty of situations where order by is justified, if not required. Just be aware there are some significant costs involved in its use, and you shouldn't get in the habit of tracking it on every query just because. Limit and offset clauses. The limit and offset clauses allow you to extract a specific subset of rows from the final results table. The limit defines the maximum number of rows that will be returned, while offset defines the number of rows to skip before returning the first row. If no offset is provided, the limit is applied to the top of the table. If a negative limit is provided, the limit is removed and will return the whole table. There are three ways to define a limit and offset: limit limit count, limit limit count, offset offset count, limit offset count, limit count. Here are some examples. Notice that offset value defines how many rows are skipped, not the position of the first row. Like limit 10 returns the first 10 rows, limit 10 offset 3 returns rows 4 to 13, limit 3 offset 20 returns rows 21 to 23, limit 3 20 returns rows 4 to 23, different from above. Although it is not strictly required, you usually want to define an order by if you are using limit. Without an order by, there is no well-defined order to the result, making the limit and offset somewhat meaningless. Advanced techniques. Beyond the basic select syntax, there are a few advanced techniques for expressing more complex queries. One of them is subqueries. The select command provides a great deal of flexibility, but there are times when a single select command cannot fully express a query. To help with these situations, SQL supports subqueries. A subquery is nothing more than a select statement that is embedded in another select statement. Subqueries are also known as subselects. Subqueries are most commonly found in the from clause, where they act as computed source table. This type of subquery can return any number of rows or columns and is similar to creating a view or running the query, recording the results into a temporary table and then referencing that table in the main query. The main advantage of using an inline subquery is that the query optimizer is able to merge the subquery into the main select statement and look at the whole problem, often leading to a more efficient query plan. To use a subquery in the from clause, simply enclose it in parentheses. The following two statements will produce the same output: select star from table A as A, join table B as B. Select star from table A as A, join select star from table B as B. Subqueries can show up in other places, including general expressions used in any SQL command. The exists and in operators both utilize subqueries. In fact, you can use a subquery any place an expression expects a list of literal values. A subquery cannot be used to generate a list of identifiers, however. Compound select statements. In addition to subqueries, multiple select statements can be combined together to form a compound select. Compound selects use set operators on the rows generated by a series of select statements. In order to combine correctly, each select statement must generate the same number of columns. The column names from the first select statement will be used for the overall result. Only the last select statement can have an order by, limit, or offset clause, which get applied to the full compound result table. The syntax for a compound select looks like select from where group by having. Compound operator, select from where group by having. And then order by, limit, offset. Multiple compound operators can be used to include additional select statements. The union all operator concatenates all the rows returned by each select into one large table. If the two select blocks generate n and m rows respectively, the resulting table will have n plus m rows. The union operator is very similar to the union all operator, but it will eliminate any duplicate rows, including duplicates that came from the same select block. If the two select blocks generate n and m rows, respectively, then the resulting table will have anywhere from 1 plus n plus 1 to n plus m rows. Intersect. The intersect operator will return one instance of any row that is found one or more times in both select blocks. If the two select blocks generate n and m rows, respectively, the resulting table can have anywhere from 0 to minimum of n m rows. The except operator will return all the rows in the first select block that are not found in the second select block. It is essentially a subtraction operator. If there are duplicate rows in the first block, they will be eliminated by a single matching row in the second block. If the two select blocks generate n and m rows respectively, the resulting table can have anywhere from 0 to n rows. SQLite supports the union, all, intersect, and except compound operators. Figure 5.8 shows the result of each operator. The compound operators union, all, union, intersect, and except. Once all of the compound operators have been combined, any trailing order by limit and offset is applied to the final result table. In the case of a compound select statements, the expressions present in any order by clause must be exactly match one of the result columns or use a column index. Alternate a join notation. There are two styles of join notation. The style known earlier in this chapter is known as explicit join notation, is named such because it uses the keyword join to explicitly describe how each table is joined to the next. The explicit join notation is also known as ANSI join notation. It was introduced when SQL went through the standardization process. The older original join notation is known as implicit join notation. Using this notation, the from clause is simply a comma-separated list of tables. The tables in the list are combined using a Cartesian product, and the relevant rows are extracted with additional where conditions. In effect, it degrades every join to a cross join and then moves the join conditions out from the from clause and into the where clause. This first statement uses the explicit join notation we learned earlier in the chapter. Select something from employee, join resource on employee EID equals resource EID, where something. This is the same statement written with the implicit join notation. There is no performance difference between the two notations. It is purely a matter of syntax. In general, the explicit notation, the first one, has become the standard way of doing things. Most people find the explicit notation easier to read, making the intent of the query more transparent and easier to understand. I have always felt the explicit notation is a bit cleaner, as it puts the complete join specification into the from clause, leaving the where clause free from query specific filters. Using the explicit notation, the from clause and the from clause alone fully and independently specifies what you are selecting from. The explicit notation also lets you be much more specific about the type and order of each join. In SQLite, you must use the explicit notation if you want an outer join. The implicit notation can only be used to indicate a cross join or inner join. If you are learning SQL for the first time, I would strongly suggest you become comfortable with the explicit notation. Just be aware that there is a great deal of SQL code out there, including older books and tutorials using the older implicit notations. Select examples. The select command is very complex and it can be difficult to see how these different clauses can be fit together into something useful. Some of this will become more obvious in the next chapter when we look at standard database design practices. But to get you started, we are going to look at several examples. All of these examples will use this data. Create table XAB, insert into X values 1, Alice, insert into X values 2, Bob, insert into X values 3, Charlie, create table Y, CD, insert into Y values 1, 3.14, Y values 1.1, 2.718, into Y values 2, 1.618, right? These examples show the SQLite 3 command line tool. The following dot commands were issued to make the output easier to understand. The last command will use SQLite 3 to print the string null whenever a null is encountered. Normally, a null will produce blank output that is indistinguishable from an empty string. This dataset is available on the books download page on the O'Reilly website as both an SQL file and SQLite database. I suggest you sit down with a copy of SQLite 3 and try these commands out. Try experimenting with different variations. If one of these examples doesn't quite make sense, just break the select statement down into its individual parts and step through them bit by bit. Simple selects. Let's start with a simple select that returns all of the columns and rows in table X. The select star syntax returns all columns by default. Select star from X. We can also return expressions rather than just columns. Select D star D as D squared from Y. Simple joins. Now some joins by default, the bare keyword join indicates an inner join. However, when no additional condition is put on the join, it reverts to a cross join. As a result, all three of these queries produce the same results. The last line uses the implicit join notation. In this case of a cross join, every row in a table is A is matched to every row in table Y. Since both tables had 3 rows and 2 columns, the result set has 9 rows and 4 columns. Join on. Next, a fairly simple inner join using a basic on condition. Select star from X, join Y on A dot A equals C. This query still generates 4 columns, but only those rows that fulfill the join condition are included in the result set. The following statement requires the columns to be qualified since both table X and table Z have an A column. Notice that 2 different A columns are returned, one from each source table. Join using natural join. If we use a natural join or the using syntax, the duplicate column will be eliminated since both table X and table Z have only column A in common. Both these statements produce the same output. Select star from X join Z using A. Select star from X natural join Z. Outer join. A left outer join will return the same results as an inner join but will also include rows from table X, the left or first table, that were not matched. Select star from X left outer join Z using A, B, A. In this case, Bob row from table X has no matching row in table Z. These columns values normally provided by table Z are padded with null, and the row is then included in the result set. Compound join. It is also possible to join multiple tables together. In this case, we join table X to table Y and then join the result to table Z. Select star from X, join Y on X dot A equal to Y dot C, left outer join Z on Y dot C equal to Z dot A. If you don't see what is going on there, work through the joins one at a time. First, look at what from X join Y on X dot A equal to Y dot C will produce, shown in one of the previous examples. Then look at how the result set would combine with table Z using left outer join. Self join. Our last join example shows a self join where a table is joined against itself. This creates 2 unique instances of the same table and necessitates the use of the table aliases. Select star from X as x1, join X as x2 on x1 dot A plus 1 is equal to x2 dot A. Also notice that the join condition is a more arbitrary expression rather than being a simple test of column references. Moving on, the where clause is used to filter rows. We can pick out a specific row, select star from X where B is equal to Alice, or a range of values between. In this case, the where expression references the output column by its assigned name. Group by examples. Now let's look at a few group by examples. Here we group table Z by a column. Since there are 3 unique values in Z.A, the output has 3 rows. Only the grouping A equals 1 has more than one row. However, we can see this in the count values returned by the second column. SQLite select A, count A as count from Z group by A. This is a similar query, only now the second output column represents the sum of all the Z.E values in each group. Select A, sum E as total from Z group by A. We can even compute our own average and compare that to the average aggregate. Select A, sum E, count E, sum E divided by count E as expression and average E as average from Z group by A. And now we can see the average as aggregate and then the other one as expression. It's the only difference is dot zero. A having clause can be used to filter rows based on of the results of the sum aggregation. When we say sum E as total from Z group by A having total greater than 500. Order by examples, the output can also be sorted. Most of these examples already look sorted, but that's mostly by chance. The order by clause enforced a specific order. Select star from Y order by D. limits and offsets and can also be applied to pick out specific rows from an ordered result. Conceptually, these are fairly simple. However, these tables and queries are available as part of the book download. Feel free to load the data into SQLite 3 and try out different queries. Don't worry about creating select statements that use every available clause. Start with simple queries where you can understand all the steps and then start to combine clauses to build larger and more complex queries. Now that we have had a much closer look at the select command, you have seen most of the core SQL language. The next chapter will take a more detailed look at database design. This will help you lay out your tables and data in a way that reinforces the strengths of the database system. Understanding some of the code design ideas should also make it more clear why select works the way it does.